In this video, I will discuss two transport layer protocols, Transmission Control Protocol, or TCP, and User Datagram Protocol, otherwise known as UDP. Now this is part one of a two-part discussion. The video will cover CCNA Objective 1.2, compare and contrast TCP and UDP protocols. Both TCP and UDP reside in the transport layer of both the OSI and the TCP IP models. Both protocols provide transport services to application layer protocols. Both protocols use port numbers and sockets to identify and multiplex communications between application processes. However, as we're going to see, the two protocols function very differently and have their own strengths and weaknesses that make each more suitable than the other for different types of protocols or different types of communications. Let's take a look at some of the differences between the two protocols, starting with TCP. TCP is a full-featured, connection-oriented, and reliable transport protocol used by applications. It has high overhead, it requires acknowledgments of transmitted data, and it requires the retransmission of data if that data happens to get lost between sender and receiver. Protocols that need the reliable features of TCP include HTTP, FTP, SMTP, and POP. UDP, on the other hand, is a very low overhead protocol with almost no features other than using port number addressing. It provides no reliable connection, no retransmission of lost data. Now this might sound bad, but this is actually perfect for applications that don't care if a few packets of data get lost in transmission. If protocols or applications need just very fast transmission of data, then a protocol like UDP is actually ideal. And applications such as voice over IP and streaming video are examples of applications that would use UDP. Now there's a couple concepts we need to discuss concerning both TCP and UDP before we go any further. The first is port numbers. A port number is a transport layer addressing element that identifies a software process running on a host machine. Now port numbers are published by the Internet Assigned Numbers Authority, and there's three ranges of port numbers that are used. There's well-known ports, reserved ports, and dynamic or private ports. It'd be a good idea to pause here and take some time to memorize the port number ranges and the well-known ports associated with applications that are shown in the table. The second concept we need to discuss is something known as a socket. A socket is comprised of three things: an IP address, a transport protocol, and a port number. Each application communicating on the network has a socket connection open to the application on the remote host that it's communicating with. In the example shown here, the client has a socket connection open to the server. That is, the IP address of the server, TCP as the transport protocol being used, and the port number that the HTTP service on the server is listening to. So those three things combine to make a socket. We've got an IP address, we have a layer 4 protocol, and we have a port number. Now, the server has a socket connection open to the client as well. And again, that's the IP address of the client, TCP is the transport protocol, and the port number that the client is listening to. By using a process known as multiplexing, a host could actually have many socket connections open at the same time to multiple servers. And those connections, of course, are being identified by each individual socket. So here we see an example of multiplexing, which is concurrent application processes. Now, each of the concurrent application processes requires its own socket, again, which is going to be the IP address, the protocol, and the port. And here in this example, the two hosts each have a socket connection open to the server. The server is multiplexing two open socket connections, one to client 1 and the other to client 2. Notice that the client starts the communication process and the server uses the client's source port as the destination port for the returned reply traffic. And then note that the clients are using the well-known port for the protocols being used, SNMP and HTTP in this case. Now I mentioned earlier that TCP is a connection-oriented protocol, and that means a formal connection process must take place before two application services can communicate over TCP. This connection process is called a three-way handshake. The client starts the process by sending a SYN message with the sequence number to the server. Now the client picks the sequence number. Here I have the sequence number identified by X, but the client picks that number. The second step starts with the server receiving that SYN message from the client. Then the server sends its own SYN message to the client with the sequence number that it picks. But it also sends an ACK message to the client as well. And that ACK message is acknowledging the receipt of the client's SYN message. And that ACK message will take the original sequence number from the client and add 1 to it. That's how the client knows that the server has received its SYN packet, because it sees that ACK message that's been incremented by 1 in the sequence number. In the final step, in step 3, the client has now received the SYN message of the server, and it sends its own acknowledgement with the server sequence number incremented by 1. Now these 3 steps complete the connection establishment for TCP. Now the protocol that's using TCP, maybe it's HTTP, for example, now that protocol can begin to communicate over TCP. In part 2, we're going to take a look at how TCP performs error recovery and flow control, and we will also compare the 2 protocol headers.